Okay. Hi everyone. My name is Young Choi, and this time I'm going to walk you through this image of Carina Nebula, one of the most active star-forming regions in our galaxy. So this is not just a pretty picture. Every color and structure here represents the real physical processes. So our team created this image using LRGB narrowband filters like L-alpha, O3, and infrared data like TUMSK and Spitzer 8 and Spitzer 24. So this allows us to see not just stars within our optical visible wavelength, but also ionized gas, temperature differences, and even structures hidden inside the dust. So what you're looking at is a snapshot of how stars form and how they shape their environment. So Carina Nebula is a typical example of a star forming region. So I would like to start with the brightest region on the right, bottom right area. You see this massive, gigantic star glowing. So this area here is powered by massive stars called O-type and B-type stars. So O-type star, the biggest guy over here, are hotter, almost like the hottest star, and emit much stronger UV radiation, so they dominate the ionization, while B-type star, the second largest one here, plays a supporting, kind of like a supporting role. So their UV radiation strips electrons from hydrogen atoms, creating an H2 region. So when electrons recombine with protons, they emit light. This is why the region glows pink from H-alpha emission. So you can also see blue and purple right here in the center and towards the left, which comes from O3 emission and indicates even higher temperatures. So this region is the main energy source driving the nebula. So now, from moving from right to left, you'll see the color gradient. So the brightest pink and purple, and then fade into deeper red, like here, and much darker regions. This reflects a physical gradient. So closer to the stars, where I see this, I assume that's the O star. The gas is hotter, obviously, and produces O3 emission, which is around 15,000 Kelvin to 40,000 Kelvin. So this area is super, super crazy hot. And farther away from that area, the gas cools off and H alpha emission around 5,000 to 10,000 Kelvin dominates around this area. So this color transition basically shows how radiation weakens as it travels from right to the left side. On the left side, you see kind of like a branching tree-like structures. These are dense regions of gas and dust that have not been fully ionized. Radiation and stellar winds from the central stars, right here, erode their outer layers, shaping them into pillars. Like here, you see these kind of like a pillars and filaments, like these filamentous structures on the top. These are dense regions of gas and dust that have not been fully ionized. You know, the protons and electron stuff that I explained earlier on, that has not happened yet. So radiation and stellar winds from the central stars erode their outer layers, shaping them into pillars and filaments. So the bright edges show active ionizations, while the interiors remain dense and cold. So these regions are important because they are likely sites of future star formation. You know, as we learned in the lecture and we went through the processing, the Spitzer 8 band shows the worm dust that has been heated by nearby stars, and the Spitzer 28 traces the cooler dust. And the 2MSK band allows us to see stars that are otherwise hidden behind the dust. But, I mean, so when these IR layers are turned on, they actually fill in or illuminate regions that would otherwise look dark in the visible light. That's this version. So now let's do something important. We turn off the IR layers, the all three, Spitzer 8, Spitzer 24, and the 2MSK band filter in the afterglow. And when we remove these, what becomes much more obvious are the darker dust clouds right here. Each of these infrared filters is designed to reveal something hidden. And this is more like a raw image, I would say, because we don't have the IR filters anymore. And you'll notice the darker patches throughout the image, especially in the middle left areas, middle right areas. These are regions filled with dust. Instead of emitting light, this dust absorbs and blocks it, which is why they appear super dark here. However, these are not empty spaces. They're very dense area, maybe, but presumably some of the densest part of the nebula. At visible wavelengths, we can't see through them, but IR data allows us to peek inside and detect stars like this that are otherwise hidden. So this is a classic example of star forming region. Okay, so we move on to our next nebula of interest. This is a very different type of nebula. So it's called Spaghetti Nebula. I'll tell you why it's called spaghetti later on. Unlike Carina Nebula that we saw before, which is star forming region, this is a supernova remnant. So basically that means we're looking at the aftermath of a massive star that exploded. So instead of seeing new stars forming, we're seeing gas that has been violently pushed outward by a shockwave. That shockwave compresses and heats the surrounding gas, causing it to glow. So this image is not about birth, it's about what happens after a star dies. Let's start with the most obvious feature, the long reddish filament, as you can see right here, like the whole diagonal feature. This is not just a cloud of gas. This is more likely the part of expanding shock front from the supernova explosion, like the whole diagonal area from top left to the bottom right. That that heated gas becomes ionized and emits light, especially in hydrogen, which is why I see this in kind of like a reddish or orange color. So this is the filament. This filament is essentially a visible trace of the explosion's impact on its surroundings. If you look closely along the filament, you'll notice that it's not smooth. Some parts are like brighter over here and here, some parts being darker and thicker. This area is much thicker and this is much thinner. This tells us that the gas around the supernova remnant is not uniform. This is what makes this one special. When the shockwave hits denser regions, the gas becomes more compressed and emits more lights, making those sections appear brighter. So the variations in the brightness here are not random. They kind of reflect the differences in the density of the interstellar medium. So while Carina nebulas showed us how stars are born, the Spaghetti Nebula shows us what happens after they die and how that process reshapes the surrounding galaxy.